The thing is that we do acknowledge that whatever physics is going on in terms of the shock turbulence interaction and so forth is finally dictated by the conservation laws of mass momentum energy. Okay, and these are fundamental laws that are always valid. So basically we are putting all our money into the fact that we believe in the conservation equations, and if we can solve the conservation equations accurately, then we can predict and understand and elucidate any physics that we are interested in. Okay, so really all our challenge is in solving these conservation equations accurately. Okay, the underlying conservation equations of mass momentum energy. We are not necessarily saying that those are the partial differential equations that we begin with. We're simply saying, conservation laws, which for example says that mass in minus mass out should be satisfied at steady state, or energy in plus energy heat in plus heat generated must be equal to heat out at steady state. Those kinds of laws. Okay. Now, whether they are accurately represented by partial differential equations and whether the solution of the partial differential equations in turn satisfy those laws, that's a separate question. Okay, but if we believe in those conservation laws and we are accurately able to conserve each quantity that we are looking at, mass, momentum, energy, and so forth, then we can safely say that, okay, whatever physics comes out of that interplay of the conservation of those quantities is realistic, okay, is what it should be. Okay. So, of course, in this class we are solving partial differential equations, and we do believe from our basic knowledge of these subjects that partial differential equations adequately represent these conservation laws. Okay. Now, one thing you have to always realize, and this is something it's kind of a very subtle point, is that suppose I look at a differential equation, let's say the conservation of mass for a fluid. Okay. Now, when I say it's a differential equation, what does it mean? It means that it has satisfied the conservation law on a fluid element which is infinitesimally small. Okay. Now, whether that equation is accurate or not, there is no way to test it, because you cannot perform an experiment on an infinitesimally small control volume and test your conservation equation and say that, okay, this equation works or it doesn't work. Okay, you can only test it on a finite sized control volume. So there is a leap in faith, so to speak, when you go from an infinitesimal control volume to a finite sized control volume and say that, okay, this equation is also valid for the finite sized control volume. Okay. So we are taking a leap in faith there. We don't know for a fact that, okay, this partial differential equation that I started off with, it has been experimentally proven. No, it's just laws of calculus that we have used. In fact, the way these partial differential equations are derived is in the reverse format. You actually set up the conservation laws for a finite sized control volume, and then you use the laws of calculus to get down to the differential form. Okay. It's the opposite. It's not, the other way around. Many textbooks, in fact, they actually do these energy and mass balances over differential size control volumes. But the fact of the matter is, conservation laws are not tested, have never been tested experimentally on differential control volumes. So you have really no business in starting your derivation from that. It's wrong. Conceptually, okay, you should always start your derivation from a finite sized control volume and then get down to the infinitesimally small control volume, okay, using calculus, basically. All right, but that's a separate issue. So now, one of the things is that if you have a given computational domain, the final solution must satisfy local conservation as well as global conservation. In other words, if you have a computational domain and it's broken up into smaller computational domain or smaller volumes or domain control volumes, in each control volume you must satisfy mass momentum energy, and then globally also you must satisfy mass momentum energy. Okay. Now we will see, I'll show you an example today at the end of today's class, which will show that that's not always necessarily the case. Okay. Depends on the method you're using. All right, so one thing I want to show you is, suppose I have a partial differential equation like this guy, Poisson equation that you've been solving, okay? What is its relation to the physics? Why are we even bothering about solving these kinds of equations, okay? So that's the point I want to first touch upon. What is the relationship of such equations to actual physical problems? Now, in finite difference methods, we satisfy this equation on individual nodes. So what do? We have a computational domain. We have a bunch of nodes which are interconnected, okay, like that. Each node shares information with other nodes, and we satisfy the governing equation at each of those nodes, okay? And by doing so, we pretend, or we hypothesize, that we have automatically satisfied global and local conservation, okay? So the question is that adequate, that the fact that we are satisfying the conservation equation at each of these individual points, okay? Does that automatically imply that we satisfied the global conservation law or the conservation law locally, okay? So to answer that, we need to first understand what physical phenomena or conservation principle this equation right here represents. What is it we are conserving, and how does that work? Okay. All right. So now I'm going to generalize that Poisson equation a little bit, okay, and now go back sort of and take a different approach. I'm going to start with a physical approach rather than a mathematical approach, okay? So physically, let's say we want to solve a heat transfer problem, okay? And let's say conduction is the only mode of heat transfer. So my heat flux, you all know this from your heat transfer knowledge, is given by the Fourier law, which is negative k grad T, okay? These kinds of laws are abundant or fairly prolific in all of physics, okay? I mean, this is heat flux. Here you have mass flux, which says that mass flux is proportional to the gradient of the mass fractions, or the concentration gradient, okay? Then you can have current conduction, Ohm's law, which says that current density is proportional to the electric potential, okay? So all these laws basically say that the flux of a quantity is proportional to some gradient of the driving potential. The driving potential could be either temperature in the case of heat, could be voltage in the case of current, could be concentration in the case of mass, okay, and so on. There are other laws also which fall into this category, okay? And this is basically known as a gradient diffusion hypothesis, which basically says that any transport by diffusion follows a gradient, okay? The minus sign in front of all these laws ensures that these laws satisfy the second law of thermodynamics, which basically says that, okay, Q is proportional to gradient, but which direction is it going to go? It's going to go from high temperature to low temperature, okay? Mass is going to go from high concentration to low concentration, and so on. That's what the minus sign enforces, okay? That's the only reason it's there. Okay, so basically we are saying that there are a whole bunch of laws that follow this kind of a framework, where we say that the flux is proportional to gradient, okay? Now let's move on with that knowledge, and let's say we now consider a conservation equation of energy in a solid body. The reason I'm saying solid body is because we are only going to take conduction into account, okay? And we are going to assume that conduction is the only mode, no external work, steady state, and so forth. So in this case, we can write a conservation law, a statement, which says rate of heat transfer into control volume plus rate of heat generation inside control volume must be equal to rate of heat transfer out of control volume, okay? We all agree with that. This has been proven experimentally. People have done experiments and they have found that this is true, okay? There is no ambiguity with regard to that. Now, this control volume that we're talking about, this is a finite sized control volume on which you can perform an experiment, okay? So this is my conservation law written mathematically, okay? the units of this equation is whatever the quantity we are trying to conserve per unit time. So if it is heat, then it's joules per second. If it's mass, then it's kg per second, and so on. Okay. If it is current, it will be amperes per or coulombs per second, and so on. Okay. So that's what we are looking at. Now, what I'm going to try to do is now express these guys in terms of these flux vectors that I defined here, right, in the previous page. So here's, let's say, a flux vector. This is a heat flux vector of heat going out, I'm showing, at the surface of a control volume. Okay, surface normal is pointing this way. So Q dot N therefore represents the normal component of the heat flux that's going out. Okay, if I take that now, that of course has units of joules per second per meter square, because this has units of watts per meter square heat flux. Okay, if I multiply it by that differential area, if I call that dA, okay, if I multiply it by that and then integrate over the whole surface, what I'm going to get is net out minus net in. Okay, I'm saying net out minus in rather than in minus out because my surface normal is pointing outwards. So my sign convention therefore should be that out is positive and in is negative. Okay. In some other point in the surface, I might have my heat flux vector pointing this way. Okay. N is still pointing that way, outward. So here Q dot N will be negative. That's an example of heat going in. This is an example of heat going out. Okay. If I sum everything together, I should get out minus in. If that number is positive, then net is going out. If that number is negative, then net is coming in. Okay. Everybody follow that? Any questions on that? So this represents the net heat transfer through the boundary of the control volume, out being positive. Okay. And now we substitute it into our energy conservation equation, which I had on the previous page. So if you go back, this is what we are looking at. Okay, we just computed out minus in, and so I plug that in there. That's what my equation comes out to be. Okay, this is still a conservation equation for that arbitrary control volume that I've drawn. Okay. This equation has units of joules per second. Now the heat generation rate, we could also write it, we can pretend as if, okay, this is a heat generation rate per unit volume times dV integrated over the whole volume. Okay, that way we can also take into account variations of the heat generation rate within the control volume. Okay, so we're going to write it as that, and so therefore my equation becomes that, and I'm going to now rearrange. Before I rearrange, what I'm going to do is I'm going to apply what's called the Gauss divergence theorem. This is a theorem that we are going to use a lot when we talk about the finite volume method. Okay, so this theorem basically says that if I have, okay, a volume integral of divergence of a vector, okay, then that becomes a surface integral of V dot N dA. So it's a theorem that helps you reduce dimensions. Okay, there's a counterpart to this which goes from 2D to 1D, and that's called the Green's theorem. Okay, sometimes this theorem, the Gauss divergence theorem, is called the Green's second theorem. Okay, but it's conversely, the other one which goes from 2D to 1D, also sometimes people call it the Gauss divergence second theorem. So it's all the same, essentially, the idea. Okay, so this is what the Gauss divergence theorem says. Now, when I apply that here, so I'm going in the reverse direction from the surface integral to the volume integral. So the surface integral now becomes a volume integral, and I get a divergence of Q. Okay, now you guys might be wondering, okay, what is this divergence? So it's very simple. In vector calculus, you have this operator, this grad operator, okay, this simply denotes, I'm just going to write it in 2D. That. Okay. So if I dot product that with some vector v, okay, that gives me ddxi that dotted with vxi plus vyj. Okay, so if you do the dot product now, you can see I dot I is going to give you 1, I dot j is going to give you 0. Okay, so in the end, this will be dvx dx plus dvy dy. Okay, that's what it means. So if I write it out in Cartesian coordinates, divergence of q simply means dqx dx plus dqy dy. Okay, everybody understand that? So let me just get rid of this so we can move on. All right. So now we combine those two terms. I've just pulled the terms together to one side, and so that's equal to 0, and therefore we can conclude that this is equal to 0. Okay. So that's still my conservation equation for a control volume. All right. Okay, let's see. So this is the energy conservation equation due to conduction only at steady state, written in differential form. Now we are going to take our heat flux vector from Fourier law, plug it into that equation. Okay, so Q becomes negative K grad T. Plug it into that equation. You end up with that equation. All right. Suppose I make K equal to constant thermal conductivity. You end up with this equation here. You can pull the K outside the derivative and write it as that. And so that becomes your equation. Okay. So what is this? That's your Poisson equation that you've been solving. So what this is telling you is that all these canonical partial differential equations we solve are basically nothing but conservation laws under certain assumptions. In this case, the assumption being K equal to constant. Okay. So that's something important to remember, because at the end of the day, we go back and say, well, we have solved the Poisson equation. Now, did it satisfy the conservation law? What is the conservation law? The conservation law in this case would be that grad T, K of course is constant. Okay, this is my Q. Q is equal to negative grad T in this case. When I sum it up over all the boundaries, does it add up to 0? Okay. If not, then that means I haven't conserved energy. Okay. So if I solve d square phi equal to s phi, which is what you've been solving, and now you compute your gradient of phi at the boundaries, which will be either d phi dx or d phi dy, depending on if you're doing it on a square slab, whichever boundary. And now you add that up over all the boundaries. Does it give you back a 0? Okay. Assuming that it should give you back the integral of s phi over the volume, but does it give you that? That's the question. Okay, because that statement is a statement of conservation. So the bottom line being, just because we have solved this using a superfine mesh and super accurate method doesn't necessarily mean that we are satisfying conservation. Okay, because nowhere in the picture are we saying that, okay, we have formulated the problem such that we are enforcing conservation. It's just something we are assuming that it will automatically do that. Okay. All right. So So in finite difference, we satisfy this equation on individual nodes within the computational domain. But as I said, that does not guarantee that the overarching conservation law has been satisfied over the entire computational domain. Okay? Or we're asking that question, that does it? In other words, are we satisfying this energy balance equation? Okay? If we are not satisfying the energy conservation principle globally, no matter how sophisticated your numerical method, it is not suitable for solution of real life physical problems. Okay? And in fact, historically, this is one of the things that led to the development of the finite volume method, because when people were solving these kinds of problems using finite difference, they found, oh, you know, I'm trying to distinguish between two devices which have efficiency of 30% and 31%. Okay, or I change something, the efficiency should change from 30 to 31%, but because I have heat leakage, I can't even distinguish between that. It's going into the error in the solution. Okay, so you have to satisfy those conservation laws exactly. There's no other way to doing that. Otherwise, it's not a realistic tool, analysis tool for these kinds of problems. Okay. So when it comes to developing numerical methods for solving PDEs that represent conservation laws, and as I just showed you that most canonical PDEs do, I just gave you an example of the Poisson equation, okay, the topmost priority must be satisfying the conservation law. Nothing else matters. Okay. What I mean by that is, suppose I have a problem, okay, where let's say this is, the flux here is x, the flux here is x, and the flux here is y, and here is y, okay, and your actual numerical solution gives you 1.1x, 1.1x, and 0.9y, and 0.9y. Obviously, the solution is wrong. The fluxes don't match on individual boundaries, but even the wrong solution satisfies conservation. And that's more important than the 10% error in each of these. Okay? So, whether the solution is right or wrong is not as important as whether the global conservation law is satisfied or not. Okay? All right, so in general, any conservation law may be written as this. So basically, we are saying storage is equal to in minus out. Now, the reason I'm calling this in minus out rather than out minus in is because I have the negative sign in front, okay? And this is generation. So we all know this. What is stored is equal to, or what is generated plus what is in is equal to what is stored plus what is out, okay? So the transport in or out of the control volume of phi can occur by a variety of mechanisms. Diffusion is one of them, and I explained this to you. If you now do, for example, fluid flow calculations, your J phi will be of this form: rho u phi minus gamma grad phi. Okay, this is the advective flux. This is the diffusive flux. If you now add, let's say, drift due to electric fields, okay, then you will have another term here which will look very similar to the advection, which will depend on the electric force. Okay, so for example, if you have charged particles and an electric field, okay, so you can keep adding to this flux field different mechanisms of transport. All right, but in the end, it's all going to look like this. So if I take the example of diffusion now and I write my equation this way, at steady state we are going to get that, okay, we already looked at this. So this is the equation that we are going to start with in the finite volume formulation rather than start with this equation, because this equation is nothing but with the assumption that gamma is equal to 1. Okay, so it's a more this equation is a more general version of that equation. So we are going to always start with this one. Okay, now of course, if I want to specifically do that, I can also write that as just that, and then start my formulation from there. Okay. Okay, now one of the questions we have to ask is, okay, we are making all this big deal about conservation. So the question is, okay, if we solve the equation analytically, does that satisfy the conservation laws? Okay, so if we start the partial differential equation, solve it analytically, does that satisfy the conservation laws? Okay, so I'm going to show you a simple example. This is basically homework 1 that you solve for, d square phi dx square equal to exponential of phi with these two boundary conditions. Okay. So if I write my solution in this form, then we can write this as 1 times d phi dx. Okay, and my j, my flux, I'm going to call it basically d phi dx. Okay, that guy. So if I integrate twice and solve this, this is what I get, and this comes out to be your fluxes at the two ends. So this is your boundary condition I've applied, and you get your C1 and C2. So this is your solution. Your fluxes at the two ends are d phi dx at x equal to 0 and d phi dx at x equal to 1. I'm calculating them analytically now. They come out to be that. Okay. The net generation rate within the control volume is the integral of the right-hand side. That's this guy. Okay, from 0 to 1, which comes out to be e minus 1. And so therefore it is clear that this minus that, or that minus this, is equal to that guy. Okay. So global conservation has been satisfied because the fluxes add up to what's generated. So the analytical solution satisfies both local and global conservation. Local because we have satisfied it in individual points inside, and global because when I integrate over it, it satisfies the conservation law. Okay. So now what is so special about the finite volume method? The finite volume method has both local and global conservation inherently built into the method. Okay. That's what it emphasizes on. So let's talk about how this method works a little bit. Today we are not going to get into too much details, but just briefly. Okay. So here is what we do. Now, in the finite volume method, in your finite difference method, your nodes were located here. Okay. In the finite volume method, all we are saying is we break up the entire control volume, the full computational domain, into smaller control volumes. In 1D, that's denoted by those dotted lines. Okay. And we are going to denote the centroid of each of those control volumes by these blue circles. Okay. And they are called cell centers. And these control volumes, we typically call them cells. Okay. So our numbering pattern now goes from 1 to n, but n is now the total number of cells, not the total number of nodes. Okay. And the surfaces that we use for bounding the control volumes, like this surface and that surface, they are known as faces. Okay, so this is just some terminology I'm introducing. Just like we used for the finite difference method, we'll also use directional indices, north, south, east, west. Okay, so for example, here I'm showing east and west. Okay. In addition, we are also going to use these small letters, east, west, north, south, to denote faces. For example, this face is denoted by small east, this face is denoted by small west. Okay, so it's the eastern face of the control volume and the western face of the control volume. All right. Any questions so far? Okay. So in finite volume, we don't solve the governing equation directly. So first thing we do is we integrate the governing equation over all the control volumes. So for example, for a generic cell naught, we are going to integrate from the western face of that cell to the eastern face of that cell. Okay. This is the left-hand side of your equation. And then on the right-hand side, we do the same thing. So we are taking the governing differential equation, integrating it first over the control volume. Okay. And then what we do is, after we integrate it we are going to come up with some result, and that result then we approximate using Taylor series expansions or whatever, like we did in the finite difference method. Okay, but this is always the first step. So now, why is conservation built into this method? And I'll show you briefly. So here are the here's my finite volume integrated result. Okay. Now, if I integrate this, you can see this is going to give me dphi dx at east minus dphi dx at west. Okay, because this is an exact differential, so that's going to give me just the result will be dphi dx, and then I'm going to go from the lower limit to the higher to the top limit. Okay, so for cell number 1, it's going to go from the east face of cell number 1 to the west face of cell number 1, and then this integral is again from west to east, and so on. So I can write the same equation for all n cells, okay, sequentially. Now I'm going to add them up. One of the things to note before we add them up is that dphi dx at the eastern face of cell I is the same as dphi dx at the western face of cell I plus 1. So here are two control volumes. Okay, so the dphi dx here evaluated at the eastern face of I, this is I plus 1, okay, is the same as the dphi dx on the western face of I plus 1. Okay, that's simply from continuity of your solution, of your flux, basically. Okay. So therefore, all these terms cancel out. You can see this guy will cancel that guy, this guy will cancel the next guy, and so on. Everything crosswise, they cancel out. And you're left with just that term and that term. Okay? So the result is this minus that is equal to, now these integrals, they all add up because this is integration over control volume 1, then the next one is over 2, next one is over 3, and so on. So I can write this as going from the western face of cell 1 to the eastern face of cell n, which is basically 0 to 1, the full domain. All right. So this is nothing but equivalent to what we derived earlier. The right flux minus the left flux is equal to what's generated. All right. So in other words, the finite volume method not only satisfies local conservation. Why does it satisfy local conservation? Because each of these equations is a conservation law for that control volume. Okay. It also satisfies global conservation, which is what we have here. Okay. One of the very interesting things is that this is mesh independent. Why? Because I could have written this equation for any value of n. So suppose I break up the control volume into just 2 control volumes. So my n is 2, capital N. Okay. So I'll have just 2 equations like this, like these two, and I'll have that term cancel out that term. So what I have is left flux, right flux, they cancel out to give me the, or they add up to give me the total produced within that control volume. Okay. So I can write this for 2 cells, I can write this for 20 cells. It's always going to give me global conservation. Okay. So that's one very important property, that the conservation property that we have of the finite volume method is mesh independence. Okay. If n is equal to 1, then the method reduces to a global control volume analysis as we do in our undergraduate classes. In our undergraduate classes, we take a turbine. We say this is one control volume, here's the inlet condition, here's the outlet condition. Okay. Find out what the temperature inside will be, or whatever it is. Okay. That's nothing but a finite volume formulation with one cell. That's all we are doing. Okay. So now, of course, there will be numerical errors in the process of discretization, which we will talk about in the next class. How to discretize these guys. Okay. But so there will be errors due to that, but no matter what those errors are, the fact is that conservation has been guaranteed, okay, in this method. So So this is, now I want to show you an example which really highlights all this, okay? And it's a very simple example, and this is really at the crux of everything. I mean, when you look at all this and you look at, you know, the formulations and all that, you think, you know, this is unbelievable. Why would this happen? But you work it out, you work out the math, and you implement the method, and you find there's a big difference between the finite difference and finite volume method. Okay, and I'll show you this through an example. So here's a simple example. We're taking this equation here, right here. Okay, so gamma is equal to 1, so we are back to d square phi dx squared. All right, and the source term I've taken as negative cosine x. The reason I'm taking it that way is if I integrate it from 0 to, I think we are solving it in the range 0 to 1. Okay, it is asymmetric in 0 to 1. Okay, so there will be something produced within that range. All right. The analytical solution is this right here. Okay, and from the analytical solution, I can also compute my fluxes by simply differentiating this expression and setting x equal to 0 and x equal to L, which will give me 1 minus cosine of 1, and then this guy, negative sine of 1 minus cosine of 1 minus 1. Okay, so those are the analytical expressions. The total amount produced within the control volume, this is integral of s phi dx, or integral of negative cosine x, which gives you that, negative sine 1. Okay, so the net imbalance, if I now work with these expressions, so this is all analytical, by the way, is, you can see the imbalance will be that, okay, which is basically your j right minus j left minus the integral of the source term. Okay, that gives you 0, which basically means that the analytical solution satisfies global conservation. Okay, now let's see what happens when we solve it using numerical methods. Okay, so first we are going to look at the finite difference method, which you all know, and this is really like your homework 1 problem, except that the source term is cosine x instead of e to the power x. Okay, here are the solutions. Okay, as a first cut, I would encourage you not to even look at this right hand side here. Just cover your eyes, don't look at that, look at this. Okay, here's the solution with just 5 grid points. So of course at x equal to 0 and x equal to 1 we have Dirichlet boundary conditions, so errors are 0, so I haven't even written them out here. Okay, here's your analytical solution, here's your finite difference solution, pretty close as you can see. Okay, the errors are very small, 3rd decimal place. Okay, even with just 5 grid points. If I go down the list now with 9 grid points on the same grid x locations, I'm now I've tabulated the values. You can see this error goes down by approximately a factor of 4. Okay, which is to be expected. We know this already, delta x squared. All right, so you can see the 438 became 109 and so forth. Okay, so this is something we know already. Very accurate answer, 10 to the power minus 4 error. And we may say, well, with 5 grid points, already 10 to the power minus 4, super answer. Okay, but now this is the crux of the matter. What happens in terms of conservation? Okay, so now you look at the fluxes. Here is your j left phase flux, right phase flux, source term integrated. Okay, and then here's your imbalance. Now the source term, in this case I integrated using the trapezoidal rule, which is what I've mentioned here. Okay, so now you see here is your left flux analytical, right and source term, and obviously the imbalance is 0. You look at the finite difference values, they're again pretty close. It's in the 3rd decimal place that you have the discrepancy, 0.459, 0.458. Okay, but the big thing is this guy, the imbalance. Okay, so we have, instead of a zero imbalance, we have an imbalance of 0.02. Now one might say, well, what does that mean? Well, this is 0.02 instead of 0.45. So that's about a 4 or 5% imbalance. Okay, each of the individual fluxes are 0.45. Your imbalance is 0.02, which is about a 5% error. So what does that mean? That means if I was solving this problem for heat transfer, 5% of the energy would just disappear in thin air. Okay? If you're trying to calculate efficiency of a device, all of a sudden your answers are, 5% wrong, which is not very good, obviously. Okay? So the common misconception is that we look at these answers and we say, well, that's a pretty accurate answer, so we are good. No, you're not good. You haven't satisfied conservation. Okay, answer may be accurate. Now, the next thing to look at is, now if we go to n equal to 9, obviously, again, these answers are very accurate. You look at these answers, now you see 459, 459, 381. Okay, this one is bad actually, 386. Okay, and then there is some difference here. Here's the imbalance. It's gone down from 0.02 to 0.005 with mesh refinement. Okay. So one of the things we find in the finite difference method is that we always have an imbalance in the flux, or we could potentially have an imbalance. And usually if we do have an imbalance, the imbalance will go down with mesh refinement. Okay, but it will never completely go away. The global conservation is not built into the method. You will still always have some imbalance. Okay, and a lot of it has to do with how your mesh looks like, where the regions of strong gradient are, and so forth. Okay, how your solution behaves. It's very, very problem dependent. But you cannot ever say with certainty that your imbalance will go away. Okay. Now I want to just get out of this. I'll show you the finite volume results in a moment, but I want to kind of, let's see, draw a little picture here. Okay. So one of the things we talked about this very early on when we talked about finite difference. So suppose this problem that you are solving in your homeworks, or you have been solving. Okay, square domain with Dirichlet boundary conditions on all faces, outside faces. Okay, and here are our nodes. Okay, now one of the things we said very early on in our class is that when I have Dirichlet boundary conditions, I'm not satisfying my governing equation at the boundary. It's impossible to do that. Okay, phi is already known. We just use the value of phi. Okay, we are satisfying governing equation at these interior nodes in our computational domain. What does that mean? That means that I have actually satisfied my governing equation not in the entire computational domain, but only in this region. All this region is freely floating. I have no conservation, no governing equation, nothing I have solved in that region. Okay, I've only enforced governing equation in this region. Now my governing equation is a measure of, or it is what the conservation law gave me. Sure, it's in differential form, but be that as it may, it is what the conservation equation gave me. Okay, so what am I saying? I'm saying that in that shaded region, I'm not even satisfying any kind of conservation at all. Okay, so you get errors because of that. Okay, and that's the error that you just saw. If I refine my mesh and now I have node points here, 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 okay, twice the mesh size, what have I done? I've extended that envelope even closer to the boundary, and therefore my error reduces. Okay, if I have finer and finer and finer mesh, it's like a rubber band I'm stretching to the edge of that square, but I can't really exactly go to the edge. Okay, I'm still a little bit always far away. And that depends on where my closest mesh point is to the boundary. Beyond that, I haven't satisfied conservation. Okay, so the conservation is only satisfied up to the last node that's closest to the boundary. Okay, now one might say, well, this is only for Dirichlet boundary conditions. What if you have Neumann boundary conditions and the Robin boundary condition? And that is precisely the reason I advocated in this class that do not ever just be happy with satisfying the boundary condition itself at the boundary. You got to satisfy both boundary conditions and governing equation at the boundary. That's how you should do your formulation always, when you have Neumann and Robin boundary conditions. Okay. Now the killer is that you cannot solve a PDE or most PDEs with just Neumann and Robin boundary conditions. Generally, you need at least one Dirichlet boundary condition to anchor the solution. Okay. For example, if you take a Poisson equation, you can't solve it with all Neumann boundary conditions. It has infinite many solutions. Okay. So you have to use at least one Dirichlet boundary condition, and that's where your error will creep in. Okay. Any questions on that? Okay. So that's taking a little bit of a sidestep to understand the finite difference method, why it gives us that error in conservation. Let's now look at the finite volume solutions. Okay, so same problem, exact same thing. Here I'm using a simple summation to sum up over all the sources. This is not even a trapezoidal rule. It's really like a first order integration. Okay, just taking the source at the centroid, multiplying it by delta x. Okay, NC is the number of control volumes, n minus 1. Now one problem we get into here is that when I double the mesh size, the mesh points don't exactly coincide with each other. Okay, and that's part of the problem in depicting the solution. But you can see when I refine the mesh here, the solution gets more accurate. We've gone from 3 zeros to 4 zeros. It's approximately, again, a factor of 4 because your scheme is still second order. Okay, we haven't gone over the formulation for the finite volume method, but you will see that the interior node equations will be identical to the finite difference equations. Okay, the big difference is how the boundary conditions are done. So this is very similar to finite difference. So if I actually looked at that versus I looked at the solutions I showed you up on top, you might say, well, finite difference, finite volume, it's a toss-up, same kind of accuracy. And in fact, there are many textbooks, not necessarily on numerical methods, but physics books, which basically say the same. Finite difference, finite volume, same thing. Okay? They are not the same thing. They're fundamentally different. Okay? All right. So now you look at the flux, and this is where something interesting happens. You look at the individual fluxes, they always have errors compared to the analytical, just like you had in finite difference. Okay? And the errors will actually depend on how fine your mesh is. For example, you compare this to that versus you compare this to that. Obviously, this is more accurate compared to that when I have a refined mesh. Okay? But the big story is right here. Okay? Now, I have written zeros there, but if you actually compute it, it will be 10 to the power minus 13 or minus 14, something like that. Numerical precision, basically. But it is 0 actually up to however many decimal places I've shown there. Okay? So this is the big story for the finite volume method, that your imbalance is always 0, no matter what mesh size you use. The actual fluxes are not necessarily super accurate when you compare them to the analytical solution. They will still have errors. The actual values of phi will also have errors. But the imbalance will always be 0. Okay? So again, as I said before, it's not a question of whether the solution is right or wrong. It's a question of whether the solution satisfies the basic conservation law or not. Okay? And a unique property of this method is it's mesh independent. I can do this calculation with one cell, still going to tell me that in is equal to out. Okay? Any questions? Yeah.
in case that we are interested in the integral gradients, like for example shear rate in fluid flow. So in that case we have error here, right?
Right.
And the error in finite volume is, if I'm not wrong, is higher than finite difference.
Not necessarily. It'll be comparable if you use the same order schemes. Okay.
You still have error, right?
Yeah, you will have error. I mean, if you look at this example for this problem, for example, okay, if I look at my solution, so here you get 4596, 4582, okay, with the same mesh size, I'm getting 461. So you can argue that they're comparable. You know, one has a positive error, the other has a negative error, but comparable errors. Okay, so there is nothing to be gained particularly by using the finite difference method in terms of error in the solution or of fluxes. Because ultimately the error comes down to truncation of Taylor series. Okay, and you have to understand that no matter what you do, it's math. You can't get rid of that. Okay, it will be there. If you use a second order finite volume scheme, you will get pretty much the same ballpark error as second order finite difference scheme. Okay, any other questions? Now